What I want to talk about in this video is distributed loads. Actually, we kind of glossed over this a little bit in the first chapter. I'm sorry, actually the second chapter when we talked about the 1D elements. But I want to consider how do we deal with distributed loads. Let's say we have a mesh. Well, here I'm drawing a Q4 mesh, right? And we have some defined traction that's distributed along the edge, and it has some distribution. Let's call it T, and then let's give a dimension in this direction, X. Now for now, I'm just going to kind of consider distributions on straight edges. My derivations can be a little off for curved edges, but I think it's close enough. And most of the stuff we deal with is straight edges. The math gets a little bit much for the curved edges. Now, one temptation might be just to put point loads at the nodes. And in fact, no matter what you do, you're going to end up having point loads at the nodes. This is the KD equals F, right? We've already shown that that's the discrete finite element equations. So how does this distributed load correspond to the discrete nodal forces F? All right. Now, as it turns out, for elements that have two nodes on an edge, like the Q4 or even the constant strain triangle, what you find is actually you put half the force on the edge onto one node and half onto the other node. All right. There's actually a couple little subtle differences with that, and also when we talk about elements that have more than two nodes, we don't just divide it up into three, okay? So I want to talk a little more rigorously about how we handle these things. All right. So where does this come from? Well, last time we derived this from these equations from a minimization of energy. So let's just first write the external work done by these forces. So let's call this boundary gamma, oops, that's not a gamma, gamma T. That's the boundary where the traction is applied. So the work done by those forces is the integral over that boundary of the traction times the displacement. All right. Now when I write x here, let's assume where x is aligned with the edge. It doesn't have to be, but I want to deal with transformation of coordinates. And this displacement is the one in the direction of t. So this could be the displacement in the y direction, and this would be the traction in the y direction or in the x direction. Okay. We can also think of it just as the displacement in the normal direction or the traction in the normal direction. Okay. So this is the total work done. All right. And now this displacement is interpolated by the finite element shape functions. So I can write this as the row vector of shape functions multiplied by the nodal displacements, or I could also write it as the row vector of the nodal displacements multiplied by the column vector of the shape functions, basically the dot product of those two. We'll leave this as a known function. Let's assume we can do this. Now, it's also a little difficult. Let's just look at this element. It's a little difficult to deal with a global coordinate system X. So I'm going to do a local element coordinate system transformation. So I'm going to define a coordinate system S, where at one node S is 0, and at the other end of the element S is 1. Okay? So if this is the length of the edge, LE, I can write dx is basically length of the edge, ds, right? If we change s as 1, multiply the length, that gives us the change in x. So now we can transform this external work to be the integral from 0 to 1 of the known traction times the shape functions times the length of the element, ds, and out front, I'm going to pre-multiply by the nodal unknowns. Okay? So this is a column vector, this is a row vector, right? This term here is dx, traction times the displacement. I just pulled the nodal values out because those are constant. Let me get this little mouse cursor out of the way too. All right. Now, when we got these equations, we got this by taking the derivative of the total energy or the total work with respect to the nodal unknowns. And we wanted to minimize that and set that equal to 0. It's a vector. Okay? And that's how we arrived at these equations. So let's look at when we take the derivative of this with respect to d. Well, when you take the derivative of the external work with respect to the nodal values, you can see they just show up here. So this just leaves me with the integral from 0 to 1, the column vector of the shape functions times the traction, the given distributed traction, times the length of the element, ds. All right? So this quantity here is actually the external force, this external force, right, that arises from the distributed load. So this is the equation, okay? So you can use any element you want, put in the shape functions on that edge, and then for any given traction, you can then compute the external forces. And these would be nodal values that you then would apply on the nodes, okay? So let's do a real simple example. So let me just rewrite this. Right? The external force is equal to the integral 0 to 1 shape functions times the given traction, and actually that really should be in terms of s now, length of the edge, ds. Okay? That's what we're going to use. All right? And actually, maybe I'll pause the video here and then I'll pick up and do an example in a second, okay?